All right, welcome back, everyone. We've reached our final session of the day, nuclear power. More states are exploring proposals for a new generation of small nuclear reactors to meet their energy needs, including our neighboring state of Wyoming. What are the challenges and complexities of nuclear power? We're joined by Edwin Lyman to explore the topic further. Edwin Lyman is a director of nuclear power safety at the Union of Concerned Scientists. Dr. Lyman is an internationally recognized expert on nuclear proliferation and nuclear terrorism, as well as nuclear power safety and security. He is a member of the Institute of Nuclear Materials Management and has testified numerous times before Congress and the Nuclear Regulatory Commission. Since joining the Union of Concerned Scientists in 2003, he has published articles in a number of journals and magazines. Dr. Lyman also co-authored the critically acclaimed book, Fukushima, The Story of a Nuclear Disaster. Great to have you. Welcome, Dr. Lyman.
Yes, thank you so much for having me. I really appreciate the opportunity. How's my sound?
Sounds great.
Okay. Okay, let's see what happens here. Okay. Can you see my screen?
Looking great.
Okay, I may have to turn my video off if the sound gets funky. Can you let me know?
Will do.
Okay. So I was asked to talk today about nuclear power, so I thought I would focus on the issues that I care most about, and that's primarily safety and security and its implications for the state of Montana. A little bit about Union of Concerned Scientists is we've been around more than 50 years. We were founded by physics graduate students and faculty at the Massachusetts Institute of Technology in 1969. And our focus is using science-based approaches to address the most serious public policy issues of our time. We have about 500,000 supporters and or 500,000 members and other supporters. So nuclear power, the big picture is that it is a low carbon electricity source. When it's operating to generate electrical power, it does not emit carbon dioxide. The fuel cycle to produce nuclear energy does generate some carbon, and that depends a lot on uranium mining and milling and particular details of how those operations are carried out. So there is some carbon. It's not carbon free, but it's low carbon. So it does have benefits in a decarbonized energy future, but it also poses significant risks, and those risks can't be ignored. And the one that most readily comes to mind is safety. And we've now, it's been over 10 years since the Fukushima accident in Japan. Maybe a lot of people have forgotten about it. I haven't, but that is clearly an indication of what a nuclear power plant accident can do to the surrounding population and to the country and the economy and the environment of a country. In the US, based on the industry's own studies, the risk of a core melt accident, like what happened 3 times over at Fukushima, is about 1% per year. That is, there's roughly a 1% chance that a reactor somewhere in the country will experience a core melt every year. In my view, that's too high. Now, even if a reactor is very safe from accidents, there's always the risk of terrorism, and we know that there's an ever-present threat of both foreign and domestic terrorism against U.S. infrastructure. A reactor can be sabotaged to cause an event like Fukushima or worse, where the core melts and there's a large-scale release of radiation to the environment. In addition, some nuclear reactors, not in the US right now, but around the world, use fuels that, if stolen, could be directly used in nuclear weapons, and that's an even greater threat. There's also the issue of nuclear waste disposal. There's not much to say here because there's nothing happening in the US. There's no solution to the accumulation of spent nuclear fuel at nuclear reactor sites in the US, and that's going to be the case for the foreseeable future. Nuclear power also carries the risk of nuclear proliferation. It's a dual-use technology. The same technologies that are needed to produce fuel for nuclear power reactors to produce peaceful electricity can also be misused to produce the fuel for nuclear weapons. And so there's always that double-edged sword there. And finally, economics. This is really the biggest stumbling block for both current and new nuclear plants. And that's the fact that even operating plants today are mostly not competitive against fossil fuels or even renewables in some markets. And that's led to premature plant closures and the need for state policies to subsidize nuclear plants that may be closing before their licenses are expired. And nuclear power has suffered a lot of black eyes in the US. The only two new nuclear plant construction projects one has been a complete failure. It was the construction of two new pressurized water reactors called AP1000s, a Westinghouse design, at the Summer nuclear plant site in South Carolina. That failed so spectacularly that it's led to criminal indictments and massive fines. Its sister project in Georgia, which is two new nuclear reactors at the Vogtle site, have experienced massive cost overruns and delays. They're now running at probably more than twice the original project cost, upwards almost $30 billion now, and they're taking at least twice as long to start up as originally anticipated. Every month that they don't start up costs ratepayers and hurts the shareholders. So these were not very positive experiences for the construction of new nuclear power plants, and they show that there really is, it's not an easy task to build up the nuclear power infrastructure in this country. These are exacting projects. They require a very great attention to detail, good project management, and scrupulous attention to safety, to construction-related safety. And these projects demonstrated in many ways that they were not up to the task. So the position of our organization on nuclear power is that we've always been neutral. We don't advocate for it, but we don't oppose it either. But we do think that nuclear safety and security has to be a priority in determining whether nuclear power will play a role in the future for mitigating climate change. So it could play a role, obviously, because it is a low carbon energy source, but that doesn't mean it's essential. There's no divine right that nuclear power plants have to be part of the energy mix. They have to compete on the basis not only of cost, but also of efficiency and effectiveness in their deployment, and as well as ensuring that they meet high safety and security standards. We are seeing the possibility of broader government policies that value low carbon electricity sources, and they would, both on the state and now the federal level, and they would benefit nuclear power, but they would also benefit other ways of reducing carbon, such as efficiency, renewables, and even carbon capture and storage. So nuclear power is still going to have to compete against those alternatives, even if there's a carbon tax or production tax credits for low carbon or anything else. We believe that all these risks, safety, security, proliferation, and waste, have to be fully addressed if nuclear power is going to be credible in the future. And there will probably be a price tag associated with having to achieve that. And that price tag may make nuclear power less affordable and less competitive against other low carbon options. So one has to keep that in mind. So the landscape today is there are actually 93 operating nuclear reactors in the US. This Nuclear Regulatory Commission map is a little out of date. And we see that the Northwest and West generally do not have too many nuclear power plants. There's only one operating nuclear power plant in the Pacific Northwest in Washington State. There are research reactors and test reactors at Idaho National Laboratory and a few other facilities in the West, but generally no power reactors. But that could change over the next few years. So there is now the possibility for at least one or two new nuclear power reactor construction projects in Idaho, and the potential for demonstration reactors in Wyoming and in Washington State. And I understand that the laws have changed in Montana that may open the door for the construction of nuclear plants in Montana. And I understand those laws are in flux. I don't know what the latest is, but certainly could be a possibility. So, and looking at safety, one cannot forget the implications of Fukushima. The Fukushima accident in March 2011, in which 3 nuclear reactors melted down, exposed significant deficiencies in safety regulation, not only in Japan, but also around the world. And in response, regulators around the world, including the NRC here, required safety upgrades to address some of these vulnerabilities. But different countries did things differently. And the NRC ended up not going as far as they really should have to address those vulnerabilities, as I'll explain in a minute. And more than 10 years later, I believe that the nuclear plants operating today are still too vulnerable to the potential for meltdowns after a catastrophic natural disaster or a terrorist attack. And if an event like that does occur, that the emergency plans may well fail to protect the public by allowing timely notification and rapid evacuation or other protective measures if there's a large radiological release. And unfortunately, instead of continuing to improve safety, the NRC is focused on rolling back the way it regulates safety and security at nuclear plants, partly in response to the economic pressures on the nuclear industry. And the NRC is supposed to be immune to considerations of cost. Their mandate is adequate health and safety of the public, but in reality, they are not insulated from the economic pressures from industry lobbying and other forces that are pressuring them to essentially lighten their touch and reduce the cost to the industry of safety and security inspections and oversight. Sorry. So what happened at Fukushima? There was a huge offshore earthquake, 9.0 magnitude or thereabouts, that caused all 6 reactors at the site to lose offsite electrical power. Nuclear plants are designed to withstand a loss of offsite electrical power. They have emergency backup diesel generators that are required to be highly reliable. And at Fukushima, all of those started up. So initially, it didn't look like there'd be a problem. But 45 minutes later, the tsunami flooded the site, and that disabled most of the diesel generators as well as the electrical distribution system, leading to an almost total loss of electrical power at the site, except for limited use of batteries, including scavenged car batteries from the parking lot. This is known as a station blackout in nuclear parlance. Not a good thing. What happened, as you may recall, was that 3 of the 6 reactors melted down, and 2 of the spent fuel pools where the radioactive waste from the reactors is stored came close to experiencing a loss of cooling water, which could lead to a fire and dispersal of radioactive material. There were 3 hydrogen explosions that ruptured 3 of the reactor buildings, not actually the same 3 that experienced meltdowns through some weird twists of fate. But they led to these dramatic explosions that took the tops off these reactor buildings at units 1, 3, and 4. That did lead to fairly massive releases of radiation to the air and water, not as great as the Chernobyl accident in Russia in 1986, or Chernobyl accident in Ukraine in 1986. But still significant, making it the 2nd largest release of radiation due to a nuclear accident in history. There was radiation ejected into the atmosphere that spread over the landscape, and also radiation that was leaked into the sea, and that actual leakage continued today. Now, today there are ongoing major environmental hazards at around the site. One of the largest is the accumulation of a huge volume of radioactive cooling water. The reactor cores are still hot, and water still has to be pumped through them to keep them from being further damaged. That water is becoming contaminated and leaking out of the reactors. It's being collected, it's being filtered, and it's being stored in huge tanks on the site. That tank farm has grown enormously in size. And now the Japanese government has decided that they must release that water into the sea because of the hazard it's posing to the workers there who need to decommission the site. 160,000 people were displaced from their homes, and many thousands still have not returned. And the economy of Japan was severely damaged. Total estimates of the economy would exceed $200 billion. You can read more about accident and the response in the book that I co-authored in 2014, Fukushima, the Story of the Nuclear Disaster. So after Fukushima, the NRC required nuclear plants reevaluate their flooding and their seismic hazards. And in addition, plants acquired portable equipment, which is known as FLEX, which would be used in the event that there were a long-term loss of electrical power, as was seen in Fukushima. But the NRC did not go all the way. It did not say that that equipment had to be protected against earthquakes or flooding that might exceed what the plants originally assumed were the worst hazards that they could experience, and not so that equipment doesn't have to be protected against the actual hazard. And the problem is that the actual hazard, whether it's flooding or seismic risks or many other dangers, including tornado winds, that almost every nuclear plant site in the United States may face more severe floods, more severe earthquakes, or more severe tornadoes than what they were originally designed to withstand. And the fact that the NRC decided that this FLEX equipment did not have to be protected against those additional hazards means that it may not be actually available if the nuclear plant experiences a severe flood or earthquake in the United States. And that really undermines the whole basis for why this equipment is there in the first place. COVID-19 in the last year and a half has also affected the way the NRC inspects nuclear plants. It put great constraints on the ability of inspectors to visit and conduct detailed inspections as they do at nuclear plants, relegating many inspections to remote inspections where the licensees themselves, the plant owners, personnel would carry laptops around, and the inspectors would have to monitor those over Zoom or whatever platform. That type of inspection has significant limits on what inspectors can actually see and do. Luckily, it doesn't appear that COVID has had a significant safety impact on the nuclear fleet, but there are some things that are being baked in today: delayed maintenance, delayed inspections that we may be paying the piper in a few years for those impacts. Now, getting to new reactors. So the nuclear power industry today is based on a design called the light water reactor in the US and most places in the world. Those are typically on the order of 1,000 megawatts of electricity, and they use ordinary water as a coolant, and that's where the name comes from. And the temperature of the coolant is the coolant's under some pressure depending on the design, but it's typically around 500 or almost 600 degrees Fahrenheit. Light water reactors use fuel that is enriched. Now, natural uranium, when it's mined out of the ground, does not have a high enough proportion of a certain isotope called uranium-235 to sustain a chain reaction. In other words, to have a self-sustaining generation of power with using light water as a coolant. So it has to be enriched, but the fuel is typically enriched to less than 5% uranium-235. Enrichment is a fairly complex technical process to separate the uranium-235 isotope from the uranium-238 isotope and change their proportion. Now, the good thing about light water reactors is that this fuel is not directly usable in nuclear weapons. So if it were stolen or diverted by an adversary who was seeking to build nuclear weapons, they would have to have their own enrichment plant to further enrich the fuel to use in nuclear weapons. Now, of the roughly 450 or so operating nuclear plants in the world, all but one, these are power reactors, I should say, all but one are water-cooled reactors. So there's very little industrial operating experience with other types of reactors, as we'll discuss. Now, what's the problem with the light water reactor? Well, nuclear power is stagnating today in the world, and especially in the last decade, the number of new nuclear reactors that are being built is not enough to offset closures of older reactors, and so the numbers remain fairly stable. So the prospect for current generation plants, at least the way they're being built today, to start taking over and substituting capacity for retiring coal and other fossil fuel generators is not very good. So some people believe that the problem is the light water reactor. They think that all the problems we've talked about are what's holding it back, and that there are alternatives that can do better. So some reactors, they claim, will be passively safe, that you don't need operators to do anything. If there's a challenge to the plant, they'll just shut themselves down. They might use uranium more efficiently than light water reactors. They may deal with the nuclear waste problem. They claim that the waste can be recycled or even burned safely away. They claim that they can be built and deployed at a much reduced cost in a much shorter time. And since in some cases, their outlet temperature would be higher, and they claim they can be used for doing things other than generating power, electrical power. They could be used to produce hydrogen. They could be used as industrial process heat. And these days, even mining Bitcoin, which doesn't necessarily require higher temperature, but it does require a lot of electrical power. Let's go forward. So what are the alternatives to large light water reactors? You can have small reactors, and these are called small modular reactors. They could be light water, or they could be something else. But the main SMR design moving forward today is called NuScale. And the current concept would be a module that would only be about 77 megawatts of electrical power, so more than 10 times lower than conventional plants, and they would be built in packs of anywhere from 4 to 12 units. Now, you could have reactors that use coolants other than water. You could use a liquid sodium or any other type of liquid metal. These are called fast neutron reactors, and I can explain that later. But they have significantly different properties from light water reactors. And there are two fast neutron reactors that are now under serious development. One is called Oklo, and that's a very small or micro reactor. And actually, there's a mistake here. I'm sorry. To clarify, Oklo is not liquid sodium cooled; it's liquid potassium cooled, but it's a fast reactor. TerraPower is building or has proposed to build a demonstration fast reactor that it calls the Natrium. There would be a 345 megawatt electric plant with an energy storage unit that could boost that to 500 megawatts when power demand is higher. Then you could have high temperature gas cooled reactors using a gas like high pressure helium. And these can operate at much higher temperatures than a light water reactor. And X Energy is a company developing a high temperature gas cooled reactor called the XE100. And these would be 80 megawatt units that would be built in packs of 4. And then you can even have reactors that instead of having a solid fuel would have a liquid fuel. And that is called the molten salt fuel reactor. And there are a number of developers who are proposing to build this type of reactor, most prominently a company called Terrestrial Energy that would have a molten salt fueled reactor of anywhere from 200 to 400 megawatts. So what are the prospects here in the West? So NuScale has proposed to build a plant at the Idaho National Laboratory that would be funded partly by UAMPS, which is the Utah Municipal Power Systems Collective, or some members. And that plant could be up and running around 2030, according to their current schedule. Then there's the Oklo reactor, micro reactor I referred to, which is tiny. And it's not clear right now when that plant may actually be built. It's currently in review by the NRC. Then the US Department of Energy in 2020 got money from Congress for an advanced reactor demonstration program, and that includes funding on a 50-50 cost share basis for 2 demonstration reactors. And those awards were given, one to TerraPower for the Natrium fast reactor, and the company announced it would be building that at one of 4 former coal sites in Wyoming. The Congress required that it should be built and operational within 7 years of its award, which would mean 2028. But everyone acknowledges that that's a very, very aggressive schedule. The other demonstration project award went to X Energy to build a minimum of 4 of the XE100 reactors in Washington State, probably at the Columbia Generating Station near the Hanford site by 2028 as well. Now, these projects are only going forward because they are getting substantial subsidy by taxpayers, a total of billions of dollars if they're completed. Because no nuclear power plant today in the US is economically viable based on cost competitiveness alone. Now, that's not necessarily a bad thing, again, because if we assume that there's a cost of emitting carbon and low carbon generators are being penalized by not having the benefit or not having that value. But again, you need to be able to compare these projects to other alternatives or low carbon alternatives that may be less complicated, may be less risky. So small modular reactors, and I may have gotten my 5-minute warning here. No, okay, not yet. Actually, I've gone over, haven't I? So SMRs are believed to be more affordable than conventional reactors because they're smaller, but that doesn't mean they're cheaper. And so NuScale, for example, as a 77 megawatt plant, will have a major cost disadvantage because of economies of scale. If all other things are equal, if you shrink a nuclear power plant, it's going to generate more expensive power. So based on that, if a NuScale module were essentially a reduced scale copy of a large light water reactor, the cost would be nearly 5 times greater than what that large reactor would produce. Now we know it's not a carbon copy, but we don't know how different it's going to be because there are a lot of decisions that still have to be made about the way it's going to be constructed and operated. And the SMR vendors are generally lobbying for much weaker safety and security requirements in order to try to reduce their capital and operating costs. And these range from not having the same large containment building as conventional reactors, not having offsite emergency planning requirements, having fewer or even zero operators for the reactor, having fewer or even zero security responders that can protect if there is a terrorist attack trying to sabotage the reactor. And these safety reductions, individually or in total, could offset any inherent safety advantages that the reactor provides. They could not only offset, they might even be more severe so that you're going to end up with something that's less safe than current reactors. And another thing that's important, a number of these vendors are pitching the jobs that these projects could bring to communities. But if you think about it, if there's so much cost pressure to try to reduce construction and operating costs, that's both a major factor in both construction operating costs is the cost of labor. So you can't really cut cost significantly without also cutting the number of jobs that are both in construction and operation. That's something people need to keep in mind when they hear about promises of all the employment these reactors are going to bring. Small isn't always safer, and I'm going to speed up a bit because I'm running out of time here. But even if a reactor is smaller, if you have multiple reactors at a site, you have to figure out how they're going to interact with each other in the event of an accident. And the passive safety claims of NuScale are misleading. And it turns out that there are certain potential ways that the plant could be upset that would actually lead to the potential for a severe accident that weren't originally considered in the design. And these have not been fully dealt with by the NRC and its approval. Now, new reactors should be safer. That you would think any other industry, you want continuous improvement. You're coming out with a new model. It should be safer than the previous models. But that's not true for the NRC. The NRC has an explicit policy that says we're not going to require new reactors to be safer than current reactors. And that's because they were afraid that such a policy would make it seem as if current reactors aren't safe enough. But this really stifles innovation. And that's why reactors such as NuScale can cut corners on safety. Now, a lot of people seem to believe that whether large or small, light water reactors are not the future of nuclear power. Nuclear power depends on new types of reactors that would use other types of coolants. And these reactors are they have much less operating experience than light water reactors. Some of them are novel or paper designs. They've never been built or tested even. And so the prospect that you can actually commercialize any kind of reactor like that in a reasonable period of time is highly questionable. Even more serious is that many of these reactors actually don't have safety advantages, but they have safety disadvantages, and they might end up, again, being less safe than light water reactors. And I'm going to just plow ahead here. So liquid metal fast reactors, such as natrium, in theory, the major benefit of having a fast reactor is that for technical reasons, it could breed its own fuel. That is, in theory, if you operate a certain way, you can breed more fuel than you use. And this was the dream, which is why, going back to the 1950s, scientists were so captivated by the idea of a fast reactor. Problem is that it doesn't really work, or it's very hard to achieve. And you can see that you can't really breed or even burn nuclear waste, which is the other thing that is being often cited as a fast reactor benefit. You can't really do it on a reasonable time scale or for a reasonable cost. And to take an example, so the TerraPower Natrium to be built in Wyoming, or even the Oklo Powerhouse small reactor. These reactors are generally less safe than light water reactors. They have power instabilities that could lead to a severe power excursion. That is, the power of the reactor can increase uncontrollably, similar to what was seen at Chernobyl. In addition, sodium coolant can catch fire, and there are ways to try to deal with that, but it's still a safety issue. These reactors per megawatt are going to be more expensive, and for a micro reactor, much more expensive. And they're more vulnerable to proliferation of nuclear terrorism, depending on the design of the fuel cycle. And but most significant is that the main benefit of a fast reactor historically was to produce more, to use fuel efficiently, or to produce more fuel than it consumes. But the Natrium, the way it's going to be operated, is actually going to be less uranium efficient than a light water reactor. In fact, it's going to use, you're going to have to mine more uranium to generate the same amount of electrical power, maybe several times more than a light water reactor. So the main benefit of a fast reactor isn't even going to be realized by this demonstration. And even if you try to improve the fuel, you can make it more efficient, but even a significant advancement may only get it to be about as efficient as a light water reactor. So I have a hard time seeing what the benefit of this design is going to be. Gas-cooled reactors, I really see it up here, are problematic in some ways. They claim is that the fuel they use is almost indestructible, and it certainly has high temperature resistance. So if you have an accident where the fuel heats up, it can keep its integrity longer than a light water reactor fuel, but it's not indestructible, and there are ways in which you can actually damage the fuel and have a large release. And that's a problem, because if you assume, if you put all your stock in the fuel itself to serve as the containment, so you don't have a real containment structure, but something happens and the fuel doesn't behave the way you thought it would, then you don't have that backup, that extra containment to protect you. And so, and I'm really always have more than I have time for. But in summary, my main problem with a number of these reactors is that they're being sold with very deceptive slogans. They're called meltdown proof, or walk away safe, or they spend fuel and nuclear waste. Not only are they misleading, but they're only setting up the industry for an embarrassing retraction when they don't realize these great claims that they're making. And Theranos, and if you've been following that trial, Elizabeth Holmes is the poster child for what can happen if a company makes claims that are beyond the actual demonstrated technical capabilities that they have, and how what can happen if the bluff is called, for example. So it's not a good model for the industry to make claims that it can't back up, because they may end up discrediting the industry overall, even technologies that have a firm technical basis for the claims they make. For instance, nuclear power is low carbon. That's indisputable, but that could be canceled out if these other claims turn out not to be realized. So in summary, I documented a lot of my concerns about these so-called advanced reactors in a report in 2021. The link is there, and I invite you to check that out for more information. But overall, I have not been able to substantiate that any non-light water reactor meets expectations for enhanced safety or warrants less stringent requirements for safety, security, and environmental analysis. Thank you.
Thank you, Dr. Lyman. We do have some questions, although I think you answered probably some of those questions as you've been going along as well. Now, one of the questions is, with the small modular reactors, how much water do these reactors require to operate? Maybe if they aren't, I mean, here in the West, water is a big deal. And so we have drought. Is there, even if they aren't using light water for cooling, is there a water need for them, and does that make them a viable option in a state suffering from drought?
Yeah, and this is a point of confusion. Even a reactor that doesn't use water for its primary coolant, that is the water that's circulated through the core to directly cool the fuel, those generally require water for the second stage, that is converting that heat energy to steam to power a turbine. That's the conventional way of generating electricity from heat, is you have to boil water to power a steam turbine. So there are designs that have proposed other ways to do that. Air cooling. I know NuScale has air-cooled condenser version that they want to propose for low areas with low water resources. And it is possible that for a gas-cooled reactor, for example, you could design a system that would also use a gas-powered turbine, so you didn't have to boil water. You could use another type of gas. But those are actually not well developed. They haven't been demonstrated. So it's possible, but that's not really part of the picture, at least for the first generation of these new designs.
Great. Speaking of sort of dry conditions that we experience here in the West, has there been any research regarding wildfires in reactors? I know that last summer there were some concerns about wildfires reaching the abandoned Chernobyl site. Yeah. Nuclear waste is stored on site in the US. Should there be concerns about a prairie fire or a forest fire reaching a nuclear site?
Yes, absolutely. And I should have mentioned that wildfires is certainly a type of natural disaster that can wreak havoc on anything, and a nuclear plant's not exempted. First of all, nuclear plants, as I said, they require off-site power to operate in their normal mode. So if a fire will take out power lines, or if you have to de-energize those power lines to avoid further spread, that's obviously a problem. And of course, electrical systems and just about any other safety system is going to be challenged by a fire. So you have to protect nuclear plants against wildfires like any other structure, and that certainly has to be a consideration, especially if you're siting new plants in areas where there's potential significant fire hazard.
Maybe one last question, although it could be opening up a Pandora's box, but can you talk more about the hazards such as waste disposal? I mean, that's yeah, a big piece there. Does this generation of small modulars, you were saying that there's more, potentially more uranium required, produce a certain amount of power, that increase the amount of waste. Does anything about the modular design lower the risks of nuclear waste?
Yeah, I think in generally, no. And that's a conundrum because I think the industry is aware that nuclear waste and the inability to actually manage and dispose of it after the industry has been going for more than 50 years uh, is a big concern for the public. So they've engaged in this messaging that somehow these new reactors are going to be able to deal with nuclear waste differently. They generate less waste or no waste, or they recycle their own waste, as I said. And the fact is that in almost every case, although certain designs may have certain aspects that may be improved uh, in certain circumstances, in general, no, none of these reactors are going to have significantly improved waste characteristics. Some may produce waste streams that are um, harder to deal with, that there's no experience with, and they may be harder or more risky to manage. And the claims that any reactor can recycle its own waste are very misleading because of what goes into that. In order for any reactor to, quote, recycle, unquote, its waste, you have to reprocess that waste. And that's a chemical process where you have to separate those components of fuel that can be used as new fuel from all the junk that you can't use. And you still have to deal with that other junk. And you have to turn that, the usable material into new fuel. And those processes are hazardous, they're expensive, and they have risks, including the risk of nuclear proliferation, nuclear terrorism, because some of the fuel you're separating out is plutonium, and that's a weapons usable material. So it's not the same kind of recycling that you do with your paper and bottles. It's an extremely complex, hazardous, and expensive process that is not necessarily, and probably in my view, not at all going to ever be better than directly disposing of the waste, which itself has significant environmental risks, but is more limited in scope than what can happen if you try to reprocess and reuse that waste.
Okay, actually, we do have time for one more question, but just about 2-minute response or so. Deceptive messaging has taken on a certain surprising efficacy recently. Focusing on facts may not be persuasive to the Montana state legislature. What kind of regulation could slow down their path toward adopting small modular reactors, regardless of facts?
Well, yeah, I mean, this is a problem, if we have a society where scientific analysis and argument is being diminished. It's making it harder for, on many different levels. Nuclear power is no exception. Now, states are very limited in their ability to regulate nuclear power at all. So there is something called preemption. The Atomic Energy Act gives the Nuclear Regulatory Commission essentially sole authority to license and regulate nuclear power plant radiological safety. All that states can do is they have certain environmental rights which they can exercise, but that don't have to do with radiation. So the other aspects of the plant, like the heat that it dumps into waterways that can affect wildlife, for example. So states themselves have very little authority, but they can certainly help facilitate it by providing, tax breaks and other financial means to facilitate construction of new plants. And I would just say that those kinds of incentives could be conditioned on greater safety. So it's not like the state isn't regulating safety, but it's saying if you want this money, you have to do better. You have to prove to the NRC you can do better. And that, I think, is probably legal. I'm not sure it's been tested in court, but certainly the state doesn't have to subsidize plants that have significant safety risks. It needs to think hard about those in any policies or laws to facilitate nuclear power development.
Excellent. Well, thank you, Dr. Lyman. nuclear discussions about nuclear power are fairly new to us here at Northern Plains because we just haven't had any reactors immediately in our state, and so this has been very helpful for us and starting to educate our membership and think about with potential reactor going on in adjacent states and as well as interest in Montana legislature. This is very helpful for us to going forward. So
I hope so.
Appreciate your time with us and your expertise. And I think I'm going to close out then for this Montana's Energy Summit with some closing remarks here. And so thanks again, Dr. Lyman. For 50 years, everyday Montanans organized together as Northern Plains have been fighting the good fight. At Northern Plains, we are from the plains and mountains, cities and towns. We are everyday Montanans who love where we live. We stand up shoulder to shoulder to protect this place we call home. We believe that true prosperity begins with healthy soil, land, water, and air. We believe that our families, farms, ranches, schools, businesses, governments, and communities thrive when we are good stewards of these resources. We believe that if we look beyond our fences, listen to one another, and keep our minds open, we will find creative solutions to secure a clean, healthful environment for all. We are working toward a future where we live in harmony with nature, where our economy serves the people rather than the people serving the economy, where neighbors work side by side to build a world that lives up to our ideals of fairness, inclusion, and justice. To create this future, we must act now. The actions we take today will determine the world that our children and grandchildren inherit. Working together right now, we can ensure true prosperity for generations to come. So now I'm going to turn things over to fellow Northern Plains member Edward Barta for a moment.
Hi again. What a day, I'll tell you, it was amazing. I just learned so much and lots of things to think about and follow through with. One of the things that I would like to talk to you just a little bit about in closing here has to do with the Northwestern energy power plant that's being proposed for Laurel that was mentioned a little bit earlier. And I just kind of wanted to, we've sort of formed a committee to fight that power plant from going in. And I'd just like to read a statement about that and then ask you to perhaps joining us in the effort to fight this plant. As some of you may know, Northwestern Energy announced in May that it planned to build what it is called the Laurel Gathering or Generating Station in response to the statewide need for more power capacity. The station would be fueled by natural gas. This alarmed many Northern Plains members since natural gas is just a rosy way of saying methane, which is one of the leading pollutants driving the climate crisis. Northern Plains quickly formed a committee around stopping the construction of this methane plant. Originally, Northwestern Energy has sought pre-approval from the Public Service Commission, meaning that they wanted a guarantee up front that ratepayers like you and me would shoulder the financial burden of a plant that is not only bad for the climate, but bad for our health. While the ask was concerning, it allowed the public a chance to speak out and voice their concern. But on September 21st, Northwestern Energy withdrew their application for pre-approval and announced plans to accelerate the construction of the methane plant. This move effectively cut out the public, us, ratepayers, from having any say in whether or not we want this plant. The time to act is now. The public needs to be loud in telling Northwestern Energy that we won't pay for a plant that creates financial risks for energy customers while jeopardizing our health and future. Montanans deserve a fair, reliable, and sustainable source of power that protects the people and places we love. Please follow the link on the screen and in the chat and sign our petition telling Northwestern Energy we won't pay to harm the planet and ourselves. So, thank you for taking note of that.
Great. Thank you, Edward. If you're not already, please become a member of Northern Plains. Northern Plains is a grassroots organization, and we mean it. Our nearly 4,000 members across Montana elect and serve as our leadership, determine our strategy and direction on our issues, and carry out the work needed to protect the people and places we love. The only thing our 4,000 members have in common is they pay membership dues. Well, and they have the values of Northern Plains as well. General membership is $50 a year, but we know these are hard times, and we don't want money to discourage anyone from getting involved with Northern Plains. So whatever amount you feel you can contribute to become a member of Northern Plains, we'd be happy to have your support. Again, you can become a member at www.northernplains.org or follow the link in the chat. Thanks again for your participation in our Montana's Energy Future Summit. Please fill out the evaluation form linked in the chat. We'd love to hear what you thought of today's event. You can also share ideas for additional events with us in that form. And if you have any additional questions, don't hesitate to contact us. You can call or email Northern Plains staff, Sydney at sydney@northernplains.org, or call 406-248-1154. Thanks again for joining us. It's been great to have you. It's been a great day. And I know we're just scratching the surface. So great, glad you could join us, and we'll see you next time.